let's go to the next stages that are 3 and 4, like from digital twin to human digital twin. Now we are coming to the analytical part of this pipeline, and to understand this, we need to understand first what is the idea of a digital twin. Like the concept of a digital twin was introduced by Michael Reeves in 2003 at the University of Michigan. In the context of a life cycle management product. And then NASA picked it up in 2012 for aircraft health monitoring. And in 2017, Reeser and Pulher made the concept, make the conceptual part of applying the same architecture to human and cyber physical system production. So, human digital twin was born at this part. The formal definition came out together in 2021 with Shengley and Nudley definition of the human digital twin as a real-time monitoring computerized system of human agents, able to emulate or simulate their characteristic and complex behavior. So then Taylor and colleagues integrate this into a maritime context in 2022 with the Mariner 4.0 framework. And in 2025, Kui and colleagues collected the term human digital healthcare engineering, as I mentioned before, the HDHE. So as the maritime specific framework that brings it all this together. So when we talk about the human digital twin in maritime context, we are talking about a real-time digital replica of a seafarer with its, the physiological, the behavior, and the environmental that update continuously and can require simulation, and you can came with some prediction from it. So this is this part. So why this kind of HDHA matters? So this is different from just logging a sensor data to a server. There are 3 capabilities that distinguish this. The first one is, the simulation. Using finite element methods and biomechanical models, you can predict how a specific seafarer body will respond to a specific workload. This is not population average. This is the simulation of the person. This is an important part. The second is personalization. Population averages are useful but coarse. An individual physiological baseline built up over months of observation can detect deviation that population level threshold will miss entirely. A heart rate of, like 95 beats per minute at rest might be normal for one person and it could be a warning signal for another. So this is interesting. There we have a prediction. This is a leap from reactive to predictive healthcare. With enough data and well-trained model, the system can flag risk before, a symptom emerge. That is a real value position, not measure, but also anticipation about something that could happen. So how does artificial, intelligence perform on maritime relevant tasks? Let's take a look to the artificial intelligence layer. So this chart came from the Q 2025 review. On the classical machine learning side, we already know there are like traditional machine learning models such as support vector machines, naive Bayes, the basic artificial neural networks, among others. So, like the classical learning models, like decision trees, reach an 82.6% on fatigue detection, support vector machines, and 80.3%. And we have others such as naive Bayes with 85.5 on stress. They all show like solid performance, but they don't perform the best. We can use like more complex models that, are like from deep learning side with hybrid, this kind of hybrid architectures. And in these cases, the numbers jump and they perform even better. Like Convolutional neural network based for mental fatigue classification reaches about 88.88%. We have this by long short-term memory-based fatigue detection that has reported 99.9%. And, when we hear this kind of detection, like the 99.9%, we need to be cautious with this because, sometimes when we work with artificial neural network, the model can be overfit, and it often does not generalize for the whole population. So we need to be careful with this kind of, achievements. Also, this kind of hybrid architectures that, like combining convolutional neural network, like short-term memory, and others, can reach about 98.35 on motion recognition task. The patterns across, this field is clear. We have architectures that are consistently outperforming single models, but you need to take something in account for this kind of things. When you work with simple models such as supervector machines and bias, simple architectures of artificial neural networks, you can use less information. When we turn into these kind of hybrid models that are more powerful, we are going to need more information. That is something that needs to be taken into account. And also, we need to take into account that, accuracy is not the same to generalization. The accuracy of 99% on a data set of, 40 subjects in a lab tells you a very little about the model will perform across individual, across conditions, across variation in the real world. So the open methodological question I will say for this slide will be, can we hit a 99%? Can we maintain an 85% across populations and environment? That is the harder part of this kind of algorithms and how to approach them.